Okay, so this is going to tell us how we evaluate a classification model. So using a confusion matrix, we can actually evaluate a classification model. This is going to be a bit of a deep topic. And what I will do is I will just pause for a couple of minutes. I will allow everybody to go through this diagram. Don't have to worry, I'll explain every part of it. But this is exclusive to classification. Okay. So until now, what were the ideas? All the ideas are very similar to what we discussed for regression, right? So the dot fit, the cross-val scores, they're all very similar in code. And again, our focus is from a code hands-on concept perspective. We're not trying to get into theory. Okay. Another interesting concept was we talked about the pair plot, feature important. That was little new for classification. This part is completely new for classification. You don't have this for regression. Okay, so give it a glance. Then I will explain in detail to you what is true positive, false negative. So next time you talk about, you're working on your networking devices, right? You're working on some network intrusion detection, classification models. So you say false positive. What is false positive there? Model predicted is a threat, but in reality, it's not a threat. So these are very, very important conversations you need to have with your customers. So next time you deploy a model, your customers will ask you that, hey, you built a classification model for me. Please tell me how many false negatives we have in the model. Okay, so we need to understand what these different jargons are. So now we look at the confusion metrics, which can be used to evaluate a classification model in a bit of a detailed manner. So far we have understood how to use just the accuracy metric to evaluate a model. And now we will look at something called the confusion matrix. So how can we evaluate a model in a lot more deeper manner? So we are taking the same example. We're taking the same use case here, the diabetes classification problem. And one of the first things that we do is we try to define some conventions, right? So whenever we are doing any classification task, we try to define some conventions. So here we are saying that we have two classes. One, we have a not diabetes class, which is 0, which is a negative class, which is we are labeling this as 0. And the second is a diabetes class, which is a positive class, which we are labeling as 1. Okay, so again, we have got two classes. One is the class not diabetes, which is 0 negative class. And the second is the diabetes class, which is 1, which is positive class. These are two classes that we have right now. And the objective of this exercise is we want to predict. The objective of the exercise is we want to predict whether the class is negative or positive, whether the model predicted diabetes or not diabetes. Okay. So this is what the confusion matrix looks like. All of you can see the screen. So the confusion matrix is basically a kind of a array. It's a kind of a metric structure where along the rows you have actuals and along the columns you have predicted. Now, where is this actual and predicted coming from? Because remember, this entire thing is coming from the training data. So first we use the training data. We build a model on the training data. So we do model.fit xtrain ytrain. So we build a machine learning model. And then on the testing data, we do the predictions. Okay, so on the training data, we build a model. So we build a model on the training data. And on the testing data, on the X test, we do the predictions. We get the predicted values on the testing data. So we are trying to test the model, right? So we try to get the predicted values on the testing data. And we try to compare those predicted values with the actual values which are part of the test data, because it's a testing data. So if it's a testing data, we know the actuals also. That is what we are comparing. We are comparing what the model predicted with what the actual results are. So remember, there are two classes. We have class 0 and class 1. So class 0 means not diabetes, and class 1 means diabetes. So the model will predict two values here, 0 and 1. And the actuals are two values, 0 and 1. And this is how we get the confusion matrix. And with respect to this, there are a few different terminologies that we get right now. We have got TN, TP, FN, FP. So TN stands for true negative. True negative means model predicted negative and prediction is also true. So a true negative will be somewhere here. This is the way to understand true negative. True negative basically means the model predicted negative. So the model predicted N, it predicted negative class, and the prediction was true. Actual was also N. So that means predicted is 0, actual is also 0. That's true negative. What is true positive? True positive means model predicted positive and the prediction was true. That means model predicted 1, actual is also 1. That's true positive. So in this data set, you've got 35 TPs. The 35 cases where you predicted one and actually also it's one. That means these are 35 cases where the model predicted diabetes and actually also the person has diabetes. So T and TP are fine. They're absolutely okay. And in fact, whatever we were discussing all this while, like accuracy, the test accuracy rather, test accuracy is nothing but Tn plus TP by total. This is actually what we were working with all this while. We never looked at Tn separately, TP separately. We were only looking at the accuracy metric, right? Now, what is accuracy? What exactly is the accuracy metric? Accuracy is Tn plus TP by total. So out of total 154 observations, there are this many correct negative predictions plus this many correct positive predictions. You're able to clearly see how many correct negative predictions, 88, plus how many correct positive predictions, 35. That is how we understand the meaning of an accuracy. But what is really interesting to know is the false positives and false negative, because this is the errors. Whatever you're seeing in green are the correct predictions. These are correct negative predictions. These are correct positive predictions. Whatever you're seeing in red are the incorrect predictions. So false negative means that model predicted negative. This is false negative. Model predicted negative and the prediction is false. So what is false negative? Model predicted negative and the prediction is false. Actually is positive. So model predicted 0, but actually it's 1. This is a very dangerous case, right? That is what confusion matrix will tell you. You can build a model and now you can understand more explicitly how the model is actually doing. You can really understand these kinds of dangerous cases. You can clearly see that, okay, you know, we can understand these dangerous cases very explicitly now. So you can clearly see that, okay, the model predicted the negative class and but actually the model predicted you don't have diabetes, but in reality you do have diabetes, which is a very dangerous case. This is a scenario where somebody who does not have who actually has the disease, but the model is missing out. The model has missed out completely the case where a person actually has the person actually has a disease. That is what we refer to as false negative. Okay, what is false positive? False positive is like a false alarm. Okay, so false positive is like a false alarm. So we are seeing something called a false positive, which is nothing but a false alarm, and you can clearly see the false positive, which means that, okay, model predicted that you have diabetes, but in reality you don't have diabetes, right? Which is I think which is okay. When in medical terms, that's, yeah, I mean it's an error, of course. It's something where we can say that the classification is not happening correctly. It's a mistake. A mistake is a mistake at the end of the day, however you try to justify. So FP is also a mistake, but it's a mistake that is more acceptable in the medical community. I mean, if you consult a doctor generally, I mean, as an example, let's say you have some cough and cold and you go to a doctor, the doctor is fine to, like, see, I mean, it's important for the doctor to not to miss anything. They might tell you that you might have a medical condition, give you 100 tests, because they want to be sure that they don't miss out anything. So in the medical fraternity, FP is okay, it's acceptable. FN is not okay, unacceptable. Even a single false negative is deadly, because this is the case where the model predicted you don't have a disease. You couldn't even diagnose the medical condition, but in reality, somebody has it. You see how important it is to know which error is costly. So ideally, FN and FP both are mistakes. Ideally, FN and FP both are kind of errors, but it's important to understand conceptually which error is kind of considered more costly. So we have to look at both these errors and we have to understand which error is more costly. Which error is more costly? Is FN more costly or is FP more costly? And we have to mitigate the errors accordingly. So whichever errors are more costly, so we have to mitigate those errors accordingly. Okay, so that's an important thing to keep in mind. So if we think that in a particular business case, if you look at network intrusion, like if you work with, let's say, a lot of network data and network threat detection, cyber security use cases. So in those kinds of use cases, again, false negative is very costly. FN is very costly. FN is unacceptable, because FN in that case would mean model predicted it is not a threat, but in reality it's a threat. See, the whole idea of cybersecurity is to prevent threats. Like, I mean, if you have a false negative situation, that's the most dangerous situation out there. FP is almost like it's accepted. False alarms we are all okay with. There'll be a lot of cases where the network will give you a false alarm. Like, if you're using antivirus products, oftentimes it will say that, hey, I think if you're using unsafe Wi-Fi's, or if you try to go to a website and some dangerous HTML is detected or some JavaScript is detected, the browsers will often warn us, or the add-ons will often warn us that, hey, I think it's a threat, so the website will not open. These are all false positives. In reality, it's not a threat, but the model predicted it's a threat. That is okay, but this is not okay. So the confusion matrix will help us understand things at that level. So far we were working with just accuracy. Accuracy was basic. Accuracy was giving us an overall picture, like, hey, on an average, how accurate is the model? So this was giving us kind of like an overall picture. So on an average, how good is the model? That was accuracy. But the moment you look at confusion matrix, now you have more granular control. Now you have more granular control into the things. You are able to understand the things more in a much more granular manner. You're able to understand the things in a more accurate way. Okay, you can. This is the idea of the confusion matrix. Okay, so you can look at false positives, you can look at false negatives, and iteration one baseline model, you can see what kind of FN and FPs you're getting, and then you can do some feature engineering. You can try to use a better algorithm. You can try to add some new features, reduce the irrelevant features. Like in diabetes, we have those, we have got a lot of irrelevant features. Remember, blood pressure, skin thickness, they are not important features. So iteration two, you can remove some of these irrelevant features and rebuild the model. Iteration three, you can do something else, rebuild the model. So you can try out different methods, and you can rebuild the model in different ways. And every iteration, you try to see what are the FNs and FPs you're getting, and you try to make the model better and better and better. So that's the whole idea of what the confusion matrix actually brings to the table. And similar to that, you have other metrics like precision and recall, which are kind of like class level accuracies that you can also track. So that's exactly what I did here also. So you can see the code behind the confusion matrix. So initial part is the same. We take the data and we split the data into train and test. And on the training data, we fit the logistic regression model. dt.fit xtrain ytrain is what we do. And we compute the training accuracy and the testing accuracy. And we calculate the cross-val scores. You can see this is the cross-val scores that we computed. And towards the end, this is the code for the confusion matrix. So very simple. So based on whatever model that we have trained, the model is dt. So we simply say dt.predict of x test. So first we calculate the predicted values, right? So based on whatever model we have trained, first we calculate the predicted values. So on x test, we calculate the predicted values. And in the confusion matrix, we are simply comparing the actual values with the predicted values. So the confusion matrix is nothing but a comparison of the actual y's with the predicted y's. So we are comparing the actual y's with the predicted y's. So that is what we are doing in the confusion matrix. Okay, that's the idea. And if you see the confusion matrix right now looks somewhat like this, all of you can take a look at it. And this is exactly what we talked about now. We can relate to it. This is my 0, this is my 1, and this is my 0, this is my 1. 0 means not diabetes. This is the convention that we define here. And this is the actuals along the rows, and this is the predicted along the columns. Okay, so you can clearly see this is the number of FNs. So we have 24 false negatives. We have 24 such cases where model predicted you don't have the disease, but in reality you have the disease. There are 24 such cases where model predicted you don't have the disease, but in reality you have the disease. And there are 10 such cases where model predicted you have the disease, but in reality you don't have the disease. There are 10 such cases. So there are 10 such cases where model predicted, yes, you have diabetes, but in reality you don't have diabetes. So that's the inference we are able to get right now. Okay, so this is very important. And what we can do is now we can try different models. So now we can try, if you just see, we can try different models and we can compare. So we can build a gradient boosting model and we can compare the FN and FPs for those models.